Okay, organic chemistry 2341. This is chapter 9, section 2. We're going to continue NMR spectroscopy, and we're going to talk about intensity and peak splitting. Okay, so the first thing we need to think about is the intensity of the peak. It's on the graph, but let's look at what that means to us. Okay, the area under the NMR signal is proportional to the number of absorbing protons, not just the height of the peak, the total area under the peak. Therefore, the NMR spectrometer will integrate the area under the peak and print out a stepped curve or an integral on the spectrum. The height of each stepped integral is proportional to the area under the curve or the peak, and which is in turn proportional to the number of protons. Most modern NMR spectrometers will calculate and plot the value of each integral as an arbitrary unit, which means you have to use the ratio between what the NMR gives you and the number of protons you think you have to determine what the ratio of the different protons in your spectrum are. So let's take a look at that, okay? So in this spectrum here, we see that we have a stepped integral from where the NMR calculated out, and it gave us an arbitrary unit of this peak right here is 1. Okay, that's not number of protons, that's just an arbitrary number right here. And the ratio between this peak here and this peak here is 1 to 1.5. Okay, so we know we have more hydrogens than that. So how can we determine what our ratio between the two different ones are? So, well, we know that these are our benzene peaks. So we have a total of 4 equivalent hydrogens in our benzene peak. So we want to say that is 4. So we multiply this number right here by the number we have. And so that gives us a total number of 4. Okay, so knowing that our multiplier is 4, we take that and say, okay, we're looking for a total of 6 here. But our number right here currently is 1.5. Let's multiply that by our number of protons over here, which is 4 times 4, and that actually gives us the number of 6. So the relative ratio between 1 and 1.5 turns out to be also 4 to 6. So our ratio of hydrogens from these downfilled hydrogens to the upfilled hydrogens is 4 equivalent protons to 6 equivalent protons. So that's how we calculate the intensity of these, not by the height of the peak, but by the total area under the peak, and comparing the ratio between the different peaks to get our approximate number of protons. Okay, so now that we have number of peaks, intensity of peaks, and position of peaks by shift, let's talk about spin-spin splitting, okay? So spin-spin splitting occurs between non-equivalent protons on the same carbon or adjacent carbons, but it cannot be more than 3 bonds apart. So that's the hydrogen to carbon bond, the carbon to carbon bond, and the carbon to hydrogen bond. So that's a total of 3 bonds that we can go. It does not go more than 3 bonds, okay? So let's look at this compound here and start looking at how we are going to do our spin-spin splitting here. So in this case here, we have 1 equivalent hydrogen because we have 2 chlorines on this molecule here. And we have, this is a different set of equivalent hydrogens because they are together on this one that only has a single chlorine on it. So we have 1 hydrogen here and we have 2 hydrogens here, okay? So in general, what that means is these 2 hydrogens have a signal by themselves and it's going to be split by the non-equivalent hydrogen next to it, giving us this peak here. And this hydrogen is non-equivalent and therefore is split by these 2 protons to give us a total of 3 peaks here. Let's dive into that a little bit deeper, okay? So the thing we have to think about in our spin-spin splitting rules are that equivalent protons do not split each other's signal, okay? So if you're on the same hydrogen, you get 1 peak, okay? I'm sorry, on the same carbon, you get 1 peak, okay? Then we have an n+1 rule, which means that non-equivalent protons split the signal of nearby protons by that many protons plus 1. So if you have 6 protons nearby, you have those 6 protons splitting your 1 peak, giving you a total of 7, okay? Now, if A and B are, the splitting is observed for non-equivalent protons on the same carbon or adjacent carbons, okay? So if we're on the same carbon, they do not split each other, right here. These would not split each other, right here, and these do not split each other. However, both of these would split each of these carbons here. This hydrogen here will split this hydrogen here because they are 3 bonds apart. Okay, so now let's look at some common patterns we have based on how many hydrogens we have on adjacent carbons. Okay, so our simplest example here is in number 1. We have 1 hydrogen and 2 other groups on our carbon here. So those aren't hydrogens, those don't split. We have 1 hydrogen 3 bonds away from another hydrogen, and neither one is equivalent. So they are 2 non-equivalent peaks. So we get 1 peak for the hydrogen itself, and then 1 peak for the hydrogen on the adjacent carbon. So that means that A here is split into 2 peaks, or a doublet, and this B peak here is split by the A one, and so we have the 1 peak for the B, and then split by 1 proton gives us a total of 2 peaks, or we get another doublet. So when we only have 1 proton, 3 bonds away from 1 proton, we get what we call a doublet of doublets, or a doublet for one of the hydrogens and a doublet for the next one. Okay, let's add 1 more hydrogen to one of those carbons, okay? So in this case here, we have 1 hydrogen on this carbon, and we have 2 equivalent hydrogens on the following carbon, okay? So let's look at peak A first, right here. So we have our 1 peak for our hydrogen, and we have 2 hydrogens next to it. So we have 1 plus 2. That's going to give us a total of 3. So we should see 3 peaks for our hydrogen A, and we call that a triplet, okay? Now we have these 2 equivalent hydrogens. They're equivalent, so they only have 1 signal, and they're 3 bonds away from another carbon, another hydrogen that is not equivalent. So therefore it's split once, so we're getting a total of 2 peaks, which means that one, the B, is we're going to get a doublet. We're going to have our 1 peak of those 2 hydrogens split by the hydrogen 3 bonds away. Okay, so let's take that and add another hydrogen to the other carbon here. So now we have 2 hydrogens that are equivalent on 1 carbon and 2 hydrogens that are equivalent on the adjacent carbon. Okay, so if we look at hydrogen A's here, we get 1 peak for those 2 hydrogens that are on that carbon, and then we have 2 hydrogens adjacent to it, so we should get 2 more peaks from those 2 adjacent hydrogens, giving us a total of 3 peaks, and that's going to give us 3 peaks, or a triplet here, okay? So let's look at the hydrogens B here. We get 1 peak because they're equivalent, and we have 2 hydrogens next to it, therefore we're going to get 2 more peaks added to it, to a total of 3 peaks. So we're going to get a triplet right here. So that next one, we get a triplet. Okay. So notice that, again, we have 1 peak for the equivalent hydrogens on the same carbon, and then add 1 peak for each of the equivalent hydrogens on the adjacent carbon. All right, let's do that one more time. Let's start with 2 hydrogens on carbon A and 3 hydrogens on carbon B. Let's look at carbon A first. We get 1 hydrogen, because of 1 peak because of the equivalent hydrogens, and then we have a total of 3 hydrogens next to it, so we have a total of 4 peaks, and that's what we get is a quartet right here. We have 4 peaks, okay? And now let's look at hydrogen number B here, hydrogen B. We have a total of 3 hydrogens there, but they're all equivalent, so you get 1 peak, and then the adjacent carbon, we have 2 hydrogens on it, so we get a total of 3 peaks, giving us our triplet right here. Okay, so let's take this one more step right here, and let's take away a hydrogen here. So we only have 1 hydrogen on this A carbon here. Okay, so if we have that 1 hydrogen on the A carbon, we have 1 peak for that, and we have 3 hydrogens on the adjacent carbon, so we get a total of 4 peaks, giving us our quartet right here. And we have our next carbon over, our B carbon, has 3 equivalent hydrogens, which means we have 1 peak. And we have 1 hydrogen on the peak next to it, which means we have a total of 2 peaks. So we're going to get a doublet for that. So we'll see that So once you get used to looking at the carbon having the equivalence, giving us one signal, and then having 3 bonds away, how many hydrogens you have 3 bonds away, will give you the additional signals. Okay. So let's put this into a little bit of practice, okay? So let's look at this compound right here. We're going to say, okay, we have this bromopropane right here. And when we look at this, we have our CH3s right here. They have the same electronic structure around them, right? They're both bonded to a carbon with a hydrogen and a bromine on it, therefore they are equivalent. So we have 3 on the A and 3 on this A peak. So we have a total of those 6 equivalent hydrogens, okay? Now, the only other hydrogen in the system is this one here in the middle, okay? So it is a total of 1 hydrogen, but it's adjacent to a total of 6 equivalent hydrogens, okay? So let's talk about splitting these adjacent hydrogens here. This hydrogen will split these hydrogens, and this hydrogen will split these hydrogens. But since those are equivalent, those 6 hydrogens on the methyl groups here count as 1 peak because they are equivalent hydrogens. And those equivalent hydrogens are only next to 1 hydrogen. So that means those equivalent hydrogens are going to be split by 1 hydrogen, giving us a total of a doublet, okay? Which means these methyl groups give us a total of this doublet here, okay? Now, we have the last remaining hydrogen here. So we get 1 signal for that hydrogen here, but we have a total of 1, 2, 3, 4, 5, 6 equivalent carbons adjacent to it. So that means we get a total of 6 additional peaks added to it, which gives us a total of 7 peaks. And if we look at our splitting here, we have 1, 2, 3, 4, 5, 6, 7 peaks right here. Okay, so the n+1 rule does apply even when they are hydrogens that are on different atoms, but are equivalent in electronic structure. Okay, so let's go and do this again with something a little bit longer here. So here we have nitropropane, okay? So in nitropropane, we have what I would say we have a total of, we have hydrogens here that are different because they're bonded to a nitrogen. So that's 1 set of hydrogens. We have the hydrogens here that are different because we have a carbon bonded to a nitrogen and then a carbon bonded to just hydrogens. So that makes them different. And then we have this carbon here that is different, okay? So let's first look at the shift right here. This is going to be shifted most downfield right here, most downfield because it's bonded to that nitrogen, that electronegative atom, okay? This one right here is going to be somewhere in the middle because it's close to the carbon bonded to the electronegative atom, and then it's close to a carbon bonded to just hydrogens. And that's going to leave our last one being furthest upfield. So just looking at what the electronic structure is, we now know they are all 3 different types of hydrogens and where they should appear on our spectrum as far as shift is concerned. Now let's look at the splitting, okay? So when we look at the splitting on the first one here, let's look at this A carbon right here, okay? And on this A carbon, I'm gonna change back to green here. On this A carbon here, we have a total of 3 hydrogens here, and 3 bonds over, we have a total of 2 equivalent hydrogens, okay? So we get 1 peak for the 3, and then it's split 2 times for those 2 equivalent hydrogen. So we should get a triplet the furthest upfield. So our A peak here should be 1, 2, 3. The 3 that are all equivalent on the methyl group plus split twice by the 2 hydrogens next to it, okay? And what we see is we do have a triplet here on A. All right, now let's look at the next one here. The next one here in the middle here, let's call those the B hydrogens, okay? So we have 2 hydrogens there, but they count as 1 peak because they're equivalent. We have 3 hydrogens on the A carbon, so that's going to give us a total of 4. That's going to give us a total of 4 peaks there. And then we have 2 more hydrogens on the other peak, which is going to give us a total of 6. So our B carbon here should have a total of 6 peaks here. And we see 1, 2, 3, 4, 5, 6 peaks here. So that's great. That's exactly what we should see. Now let's look at our last carbon here, the hydrogens on our C carbon here. So we have no hydrogens to this side here, so we don't have to worry about that. We have our equivalent hydrogens, so we get 1 peak, and then we have 2 hydrogens next to it. So we have our 1 peak plus 2 peaks gives us a total of 3, which means our last peak here should give us a total of a triplet, and that's what we see in our highest peak here. Okay, so not only do our shifts agree with where we think they should be upfield or downfield, but our splitting agrees as well. And if we were to integrate this, we would see that our ratio should be 3 hydrogens here for our A carbon. I should get 2 hydrogens for our B carbon and 2 hydrogens for our C carbon as well. Okay, now let's talk about how alcohol and amine protons react a little bit differently in the NMR. First of all, because we're going to have that very electronegative atom, they usually do not split signals, which means if you see a molecule like ethanol here, we will not see the hydrogen on the alcohol split. So what I'd like to say is we use the hydrogens on adjacent carbons, not adjacent atoms, when we're calling our splitting pattern here. So if we look at this, we would see our hydrogen that's on the oxygen is going to be all by itself and be a singlet because it's not being split by the carbons adjacent to it because it's going through that electronegative atom. So we get a single peak for C. If we look at A, we have a peak for this, and then it should be split into 1, 2 more. So we should get a triplet for that. And then we have then our last peak here, right here, should be split by only the hydrogens on the carbon next to it. So this will give us 1 peak plus 1, 2, 3, which would give us a total of a quartet. So this is our quartet here. This is our triplet here. And because we do not split through electronegative atoms like oxygen, we get a single peak for this. One other thing to note is that if your hydrogen does hydrogen bond, like in a carboxylic acid, an alcohol, or an amine, if you add a little bit of deuterium oxide to your NMR sample, you will get a proton exchange from that hydrogen bonding, and that signal will turn from hydrogen to deuterium. Deuterium is NMR inactive at this specific frequency, and therefore you will watch that peak disappear. And so this is a good way to test if your compound has a hydrogen bonding atom or not by adding a little bit of deuterium after you take your NMR and watch the signal disappear. That tells you you have that alcohol or that amine or that carboxylic acid peak. All right, so the last thing I want to talk about is the protons on benzene, okay? So if you have just benzene by itself, all 6 of those protons are equivalent and show up around 7.27 ppm. However, if you monosubstitute a benzene, that means you have at least 3 different types of hydrogens here. You have the ones that are ortho, are going to give us one type of signal. You have the ones that are meta, they're going to give us a different type of signal. And the ones that are para, and the one that is para, will give us a third signal. Now, depending on on what Z is, on how electron donating or electron drawing it is, it'll change which peaks are shifted up and down, and so you get a very complex pattern. And it varies with that. So if you look here with something like carbon, which doesn't donate or withdraw very much at all, they're kind of clumped together fairly closely, and we really can't tell the difference. If you have an electronic drawing group here, that's of course going to give you a different shift for the ortho and the meta, because think about the resonance structures and the intermediates there. So we're going to get a different peak splitting there. And then if we have an electron donator right here, we're going to get a different peak splitting. And typically we get a bigger separation when we have that. But all of these peaks should appear between 6.5 and 8 ppm. in that aromatic proton range. Okay, and that's the last of the four most important things about proton NMR, which is number of peaks, intensity of peaks, position or shift of peaks, and the splitting pattern.